I hope you watched my previous lab about the basics of Java that talked about compiling a Java program, running a Java program, and also we wrote a hello world using the IntelliJ idea, and also touched the primitive data types, which are the building block of the Java language, so that we can represent the real-time or real-world information using Java. So in this lab, we are going to talk about the data structures in Java. Data structure actually are also the foundation of any programming language. As we talked in the previous lab, Java provides different primitive data types so that we can encode the real world information like the name of the people or salary of the people or some characters, some Boolean information. We can encode those using Java primitive data types or reference type. So the data structure actually goes one step further and help us organize those primitive data types or the reference data types. So for example, I want to encode the name of the user in Amazon.com, right? Amazon.com has millions of users. So if I want to encode one user, I can simply do string variable name equals the value. But if I want to store hundreds of users, how do I achieve that? That's where the data structure comes in. So let's get started. I'm going to create a new project in IntelliJ. Okay, so I'm going to call it data structures, and as you know, we choose Java language, Gradle build, and that's it. We create it. As we talked in the previous lab, Java has standard folder format, which is src main Java. So in the Java folder, I'm going to create a new class called data structures, and as you know, everything is every class name is in Pascal case. So D is capital, S is capital. When I enter that, it will create a public class data structures for me, and you can see the file name is same as the class name. And the entry point for Java is main method, public static void main, and the main method takes string array arguments. So I just mentioned string array. Actually, that's what we are going to talk about today. So the different data structures in Java are array, we have set, we have linked list, we have map, we have tree. We also have queue and stack. So these are the data structure that we'll talk about today. And the first one, array. If I want to store the name or the username of the Amazon.com, it's easy, right? I can do string username equals to Upadhyay, right? Awesome, done. But I want to store all the users in Amazon.com, which is like millions of users. So how can I achieve that? That's where the array helps to store the collection of information. To represent an array, Java provides a small bracket, right? So I said I want to store hundreds of usernames. The data type is still a string, but it is a list of string. So I will call it usernames equals to, now I need to initialize it first. So I can initialize an array using new keyword. New is to initialize a reference data type in Java. When I create an array, I need to predefine or tell it ahead of time how many elements will be in array. So when I say that I want to create a collection of usernames, I have to tell how many usernames collecting or storing in the variable, right? Let's say Amazon has 10 users, so I provided 10. Okay, so that's the initialization. When it creates the array of 10 values, all the values, all the 10 buckets in the array will be defined empty, right? So it will be something like this. First bucket, it will be null because I haven't defined anything. Second bucket, null. Third bucket, null. So it goes like this, right? It will create a collection with 10 buckets. You can see 10 buckets here, and everything is null by default because I haven't assigned any value. So that's where I need to add values. The array data structure starts with indexing. So here we have 10 buckets here, but the first bucket is indexed as 0 and 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9. So the indexing goes from 0 to 9. Okay, so the 0 being the first element. So now if I want to assign the first value, I will do usernames bracket 0 equals to Bajai. So this will assign first bucket of the array with Bajai. And I want to add second value, which is going to be FinMan. Okay, I want to add third user, which is going to be second index, and I'll call it Bezos. Okay, so that way I can create from 0 to 9. And from the complexity perspective, the lookup is very fast, right? Because when I create the array, Java actually creates the memory block for these 10 values as a continuous memory, right? So they are right next to each other. So when I say give me first index, it will go and fetch the first index. If I ask it to add the first index, it will take the value and directly go to the first index, right? It can randomly access the first index. So adding values is O of 1. O of 1 represents the complexity of writing the value, and O of 1 meaning that it's a constant time, which is the fastest we can achieve. So now the second operation we need to do is access the value, and in order to access, just like how we wrote it, we access using the variable name and bracket sign and the index name. Let's say I want to access the first value, right? And put it in a variable. First username. If I print that value, it should print FinMan. Awesome. So accessing, as we just talked, is also O of 1, and this is because I'm giving it a index number to access the value. I gave it 1 and it directly goes to 1 and fetches what value is there. So that's pretty fast. Now if I want to search any value in array, then I have to traverse the whole array. So the search is going to be O of n. Now if I want to iterate over the array, Java provides a for loop or while loop. So how can I do that is for int I equals to 0. Okay, I'm asking it to start from 0th index and go until the end of the array, which is username.length, and each time increase the counter or index with 1. So I++ is also equals to I equals to I plus 1. We want to access the that particular index and store that in a variable name. Okay, then I want to print that value. Okay, if I run it, you can see that it printed FinMan first. Well, that comes from here actually. Then when we iterated, printed Upajaya because that was our first value, then FinMan, that was our second value, and Bezos, that was our third value. But we didn't define any of the value after the third index. So that's why the remaining values are zeros here. Okay. So the iteration is O of n, meaning that it will take any steps to complete the iteration. And arrays are used if you want a contiguous block of memory. That way all the values in the array stored next to each other. And one more thing is these values will be stored in Java as a heap memory, and that is because every different types, whenever I do new, it will be defined in the heap memory of Java. Now if I compare that with the primitive data types in our previous lab, when I do int x equals to 100, that will be actually defined in the stack memory. Now if I want to store multidimensional data like the matrix in array, we can do int instead of single bracket. We need double bracket now because we have rows but also the columns. So let's say this is simply a data matrix, and initialization goes like new int, and it needs the number of rows. The first size, let's say I want a matrix 2 by 3, so I can do 2 by 3. And in order to assign the values, I can do just like in single dimensional matrix, data matrix. Let's say I want to define the first row and first column, and that is going to be in array 0 0 because the indexing starts from 0 in array. So the first row and first column is going to be, let's say, 1, and first row and second column going to be 2. Now let's assign the second row, which is represented with 1, and first column is 3, data matrix, first row, first column is 4. Now if I want to access in single dimensional array, we just provided one bracket, right? So if I do 0, it will give me 0th index value. But here if I do 0, it will give me the whole array, which is the first record in the matrix. Now to access the first column, I need to provide the index number of the column. So if I do 0 0, it will give me first row, first column value. I can assign that into integer value. Okay, let's call it 0 0 value, and let me print that value. and you can see it printed 1 because our first row, first column value was 1. Now the limitation with array is that we have to define the size of the array ahead of time, like how many elements are there in the array. But that could be not the case what we want sometimes, right? Maybe our array, we don't know the size, it's ever growing. So that's where Java also provides a data structure called list, which has the growable size. So if you want to define an array of usernames where you don't know the size, like the Amazon has the users growing all the time, right? So what you can do is I can create an array list. This comes from Java util ArrayList. So in order to import that, you can import using IntelliJ IDEA, using in Mac, it's Option Enter. This is how I initialize the list. Now if I want to add values to the list, in the arrays I have to provide the index as well, right? Asking it to add this value to 0th index first, or some other value to first index, or some other value to 5th index. But in case of the growable list, I just have the value, and Java will internally maintain the indexing for me. So in order to add it, I do usernames list dot add and value. Okay, dot add Bezos. Okay, let's say I only have 2 values here. Complexity of adding value is O of 1, right? Because we know up to what index the data has been added. So I just need to fill in the next value in the array. And now if I want to access the value, I can access using the index. So I can ask, give me the 0th index. Okay, so now if I print this value, it should print me Bajai, right? Printed me Bajai. Now if I try to access 10th value, it will throw errors saying that there is no 10th index here. You can see that it threw the exception, index out of bound exception. It says index 10 out of bounds for the length of 2 because there are only 2 elements in the array. So to access, complexity is also fast because it already knows where the 0th index is, because under the hood this growable list still uses the array data structure. So it looks up the data by indexing. I can also remove the value in list, and I can do that by providing the index. Okay, if I give it 0th index, it will remove the value from the list. Let's say that I had one more value here, Musk, right? Now if I remove the 0th index here, right? So that means Bezos now needs to move to 0th index and Musk needs to move to the first index. So that's why I need to move or shift the values to the left. That's why the complexity is O of n. And iteration, just like how we iterated over the array, we can iterate over the array list in similar fashion. Another approach as well, which is called enhanced loop. So what I can do is I can do string username list. So it will iterate over the username list and give me the value of each iteration into username 1, and we can use username 1 to print the value for now. The next data structure in Java is called set, and just like an array, it is also the collection of the elements, but the difference is that in set you can only have the unique values. So if you have values like 1355, it will store 5 only one time. The implementation wise, the other difference is that the set doesn't have get method that we can use to access the value. So let's see the example. I want to store all the scores that a student has in all the subjects. Okay, so I need to define a set which comes from Java util. So let's import that, and since this is, let's say, scores are in integers, so set of integers scores, and to initialize I use a new keyword and has set. Okay, I import the has set with command enter, right? Or you can manually write import Java util has set at the top. Let's add values. Okay, so I add scores dot add 1, scores dot add 10, scores dot add 5, and scores dot add 1 again. So adding is quick enough, and the complexity, the time complexity is of 1, meaning it's a constant time complexity. If I want to access, I cannot access individual value, but I can iterate over the whole set using O of n complexity. Okay, so if I want to iterate over these scores, I can use the enhanced for loop or the traditional for loop, whichever you want. I'm going to use the enhanced for loop. So this is integer, so integer x of scores, and what it does is it iterates over these scores, and on each iteration it gives me the value x. Okay, so if I print the value using system.out.println x, it will give me 1, 10, and 5. The order can be random. Okay, it gives me 1, 5, 10. But you can see that 1 is only one time, and that's the whole purpose of the set data structure, that it stores the duplicate value only one time. So you can think of any situation where you only want to store the unique values, you can use the set data structure. The next data structure is the linked list. The idea of the linked list is just like an array or the growable array list is to store the collection of the elements or values. But the difference with linked list is it stores the information using a pointer to the next information. So in the array, we define the contiguous block of memory and put the values right next to each other using the index. However, in the linked list, we store the information using a pointer to the next value or the element. So every value is contained in a node, and that has the value and the pointer to the next value, right? So let's say this has pointer to the next node, and next node has value and pointer again. So it goes forever like this. The example could be list, let's say string. Let's say I want to store all the purchase items in Amazon.com, where I want to see what is the first purchase item and the second purchase item and the third purchase item, and I want to create a linked list for that. So linked products equals to new, and Java provides linked list data type. So this is the initialization. Now in order to add, all I need to do is linked products dot add. Let's say I bought Samsung TV. Okay, then I bought iPhone 14, whatever the version is. Then I brought a refrigerator. Here you can see that I'm just adding the values, but under the hood Java is actually creating a node for each of the value and pointing to the next node. If you go inside the implementation of Java, you can see the implementation says that appends the specified element to the end of the list. Okay, so it will first add a node Samsung TV and pointer to the next one is null. There's nothing. Then it will point Samsung TV to the new node iPhone 14, and similarly the refrigerator. Now adding is O of 1, right? Because if I know the last node, I just can add a new node on top of the last one. In order to access, I can simply do .get method with the index I want to access. If I want to access first index, I can. And lookup is slower because if I do 10th index here, it has to traverse one at a time, right? It will traverse first, second, third, fourth, fifth, sixth, seventh, 8th, 9th, and then 10th. So it has to traverse all the previous nodes, unlike in array where I can randomly access the index. Now I can also iterate on it, just like in other data structures. I can do X and I can use sout, that is a shortcut for system out println in IntelliJ. So I want to print X. You can see it printed Samsung TV, iPhone 14 and refrigerator. The next data structure, which is one of the highly used data structure, is a map. And map is a associative data structure. Map helps establish a relationship or association between different data types. For example, I want to store the information about how many products are sold every day. I have a day, a number of products sold, right? So I have a day and number of products sold association, and I can use map for that. So let's write a map. It comes from Java util map, and it has, you can see association has a key and the value, right? So I have to provide it key and the value. So my key is going to be local date, and value is going to be integer, and I will call it day products. And to initialize the value, I use new, and the implementation is called hasMap. And we'll talk about why is it called has in a minute. So that's the initialization. You might be thinking, why does it not need the size like in array? Right? Because in array we have to predefine how many records are going to be in the array, but the hash map doesn't by default. And now let's add the value to the hash map. So I can add the value using a put method. So I first need to put the day, right, because that's what the map is representing. So I need to do local date. It is, let's say, 23rd 01/01, and how many products sold on that day, let's say 100. Okay, similarly, local date bars, that's how I define my date, 2023rd, first month and second day. Let's say Amazon sold 300 products. So that's how I maintain the association between day and the value. And adding a value, the complexity wise, this is O of 1, meaning fast. And that's one of the reasons why people prefer HashMap, because writing is fast and also the lookup is fast. Now how it actually works when I write the value is it first creates the hash of the key. Okay, so the day here is 2023 01/01. It will first create a hash for that, hash of the key, and once it creates the hash, it will use that hash to store the value in the hash map. Okay, let's say that the hash is 15. So under the hood, HashMap is still using an array data structure we previously talked about. Right, in an array, we write to the array, we read from array using the index number. So using the hash index we just created, I can put the value in the array. So that's how it works internally. So our string, for example, has the default hash code method that you can see inside string. This is the implementation of hash code. And if there is a duplicate hash code, then the hash map will actually keep the both values if the keys are different. So here you can see that the keys are different. So even if their hash collides, the hash map will keep both values. But let's say that I put another key value, and that is same key which we provided before, 2023 01/01, and I put the value 3000. Okay, now you can see that this will have the same hash code as this first record because the keys are same, and it also will have the same hash code. So what it will do is it will go to the same hash code index and replace the value because it's a duplicate. Now to access the values, which is also O of 1, because in order to access the value I will have to provide the key and it will create the hash code. For that hash code it will go and directly look up the array. So as you know, array lookup we just talked about has the O of 1 lookup, and I can look up the value using the get method and providing the value. So it will give me 3000, right, because 3000 override 100. If I provide some key that doesn't exist, for example 15, right, I didn't provide any value, it will give me a null value back. Now in order to iterate on the map, I can use a enhanced for loop. I can do map.entry, that's the record in a map of type local date to integer, and I call it key value record, and iterate over day products dot entry set. and now I can print the key value dot get key, and I concat that with hyphen sign key value dot get value. Okay, so this should print two records, January 1st and January 2nd, with value 3000 and 300. Let's try it. And you can see it printed 01 with 3000 and 02 with 300. You can see that it didn't print in order, and that's how the hash map is. Hash map doesn't guarantee you the order of the insertion. Queue data structure helps restore the elements or the values just like in other data structure, but it stores the information in the order they come in. Okay, so for example, let's say going to a restaurant. When you go to a restaurant and there are, let's say, 10 people waiting in a line, then the way they are served is based on whoever comes first will be served first, right? And that's the idea of the queue data structure as well. So here in a queue, you can see that whoever is first in the queue will be served first, and then the second and third and so on. So let's see an example. Java has a queue data structure called queue, and let's say I want to create a queue of people, so queue of string because I'm going to use their name, and I have to import queue that comes from Java util queue. I will call it customers new, and the implementation of queue is a linked list actually, which we studied previously. And I have to import linked list as well, and I do command enter. That gives me the option to import. In macOS it might have a different shortcut in Ubuntu or other operating systems. So I created a queue, I initialized it. Now I want to add customers to the queue, and the complexity of adding is constant time because you just append to the end in a queue. Okay, so I add customers dot, let's say John came first. Okay, then I'm adding Mihail came second, and then at the end, let's say Brad came. Okay, so that's how I add to the queue. Now I need to access the data, right? I cannot randomly access the queue. That's a very important thing, right? I cannot say who is second on the queue. I don't have that capability with queue. Queue is not random access, just keep in mind. Now I want to access the data, and the way I need to access is to start from the top, meaning whichever came first I have to start from there. So it's time based, right? And when I have to access the first element, it's pretty easy, right? I know who is the first one, so the access becomes O of 1, constant access. So how can I access? I can print the value, so I can do customer dot poll. So this will actually poll the value. Okay, it will take the value and remove it, right? Because it already served the value. You don't need to be in queue anymore. If you want to be queue again, then I have to add you to the end. So that's what the polling is. It takes the value and removes from the queue. If I just want to pick, meaning that I want to see the element, but I don't want to remove it from the queue. Let's say I just want to take the name of the customer. Okay, I just can pick the information and do some operation. But both pick and poll are constant time. I can also remove the value. That is also the constant time. And I can do that using customers dot remove, which is much like the poll. Now to iterate on the queue is n operations, right? There are n elements in the queue, so it's n operations, so the complexity is O of n. And to iterate on it while the queue is empty, okay? So while it is not empty, I'll keep iterating, and I'll keep holding the value, okay? So on each iteration, it pulls the value. The first time it pulls John, then goes in the loop again. It's not empty because there are two elements, and then it pulls Mihail, and then it goes to the loop again. It's not empty, and then it pulls Brad. Then it becomes empty, and then the loop ends. So I have 3 iterations. Now if I run it, I'm removing here, so the while loop should only have 2 iterations, Mihail and Brad. You can see that. Awesome. So that's the queue data structure. There is one special case of queue data structure, and that is a priority queue. The difference is that in the queue, as you remember, we access the value in the order they come in, right? So the time is the priority here. But in the priority queue itself, the priority could be anything other than time. And the example could be, let's say, the emergency department of the hospital. Right, when the patient come in, they are put in a queue based on the medical condition of those patients. If the condition is critical, they will be put first. If their condition is, not that bad, they will be put at the end of the queue so that they will be processed in that order. So priority queue is super important, and as you can see, when the new patient comes in, you have to reorganize your queue. While in the regular queue, you just put the values in the order of their arrival. The other example of priority queue could be, let's say I want to maintain a list of the products that are sold highest in my retail company. Right? I want to keep the queue of the hot products in my company. And the hot products, the priority is based on their number of purchases in each day. Right? Whichever has the highest purchases today will be put at the top, and the second one would be the one with the least number of purchases. So let's do that example. So I'm going to define queue of product, and I call it hot products equals to new priority queue. It comes from Java util, and I don't have a product class, so I'll create a class product, and let's say I have name of the product, and I have purchases of the product. Okay, then I need a constructor so that I can initialize it. That takes the name and purchases. I'll just call it P. So I will construct this name equals to name that I passed in, and this reference purchases equals to P, the value I passed in. Okay, so I'm create a priority queue of the hot products, and let's say I add hot products add. I add a new product. Let's say I call it Samsung S23, and number of purchases were 100 for today. Right, then hot products add new product. Another product is iPhone 15, whatever the latest version, and let's say 99 products sold today. Then also I have product LG TV and 29 products sold. I also have product Wi-Fi router and I sold in 59. Actually, let's say Wi-Fi router was sold 200 times. Now the complexity here is expensive than the queue. In queue we have the complexity of O of 1, right, the time complexity. But here each time I add a product, it needs to be sorted based on the purchase numbers, right? So the first one is Samsung S3, it keeps 100, there is no other product, so okay, Samsung is the highest. Then comes iPhone has less, good. Then comes LG TV, it has less, okay, that's still good. But then comes Wi-Fi router, so this should be at the top, right? So the sorting complexity is O of log n, which is the logarithm, and the reason it's logarithm is every time a new product is added, we need to check whether this is smaller or higher purchases than the existing product. So based on that, I need to either keep going to the left of it, which is smaller than it, or the right side of the existing product, which is the bigger. So that's why it's logarithm. I traverse half of the queue. Let's say I want to show the top 3 products. So now I need to write for loop in I equals to 1 and I less than or equals to 3 because I want to show 3 products, and I plus plus. So each time I go through the iteration, I pull the top product. Okay. So what happens is first time it pulls the top product, which is Wi-Fi router. Then it will pull the Samsung S3 because that's the second highest. Then it will pull iPhone 15, that's the third highest. And since we mentioned that we want to put the priority based on number of purchases, I need to provide a priority here. So let's say I get two items, P1 and P2, product 1 and product 2, then whichever has the highest purchases should be put first. So that means whichever P2 purchases minus P1 purchases, and if the number is positive, that will be put higher priority. I actually want to print the name of the product. So now let's execute it. Here you can see Wi-Fi router comes first because it has the highest purchases, then the second highest Samsung S3 and iPhone 15. Let's say I change the priority of LG TV as 201 and I re-execute it. That should put LG TV on the top, Wi-Fi router second, and Samsung S3 third. So that's the priority queue. It's pretty important data structure. But only the downside you can see here is the write complexity to the queue, and each time I have to reshuffle my data in logarithm time. The complexity is higher than the queue because in the queue it's O of 1, which is the constant time. Now let's talk about the stack data structure. The idea behind this stack data structure is we put the value that comes first at the bottom and the value that comes after on top of it. And if we compare that to the queue data structure, we put the values horizontally, right? So imagine we put the values from left to right as they come in, and when we access from left to right in the same order that they arrived. But in stack data structure, we put the value that comes first at the bottom, and it's a vertical data structure, right? Everything else goes on top of it. Let's use Amazon.com. And if you go to your purchases, usually want to see your recent purchases, right? Probably your purchases, like 10 recent purchases. You don't care about what you purchased in 2015. That's like 7 years ago. So when you care about the recent purchases or recent items, that's where you can use the stack data structure. The other example could be similar idea, the YouTube views, right? If you go to your recently watched videos, you'll see your past like 10 videos you watched recently. If you keep scrolling, if you care really what you watched in 2015, you can go further, but you mostly care about the videos you watched recently, so that's where stack can be used. The other example, if you use the Facebook Messenger, in the list of people you had conversation, you will see the people you had the conversation most recently on top, and then you'll see the people who you had conversation 10 years ago, 5 years ago. They will be at the bottom of the conversation list. Let's see the example in Java. Java has a stack data structure called stack, obviously, and it could be of type anything. For now, let's say I want to keep a stack of recently viewed or recently purchased products, so I'll call it stack of a string, and I import my stack recently purchased items. Okay, so it's going to be new stack, and now let's add. So recently view or recently purchased items dot the add is called push, and let's say I purchased portable charger first. Okay, then I purchased Samsung S3, then I purchased lightning cable, and at the end I purchased what did I purchase? Wi-Fi router, let's say. Okay, now the adding complexity is faster in stack, just like in cube, super fast, O of 1, right? Because I'm just adding vertically on the top, right? You just need to drop it on the top, so it's fast. Accessing is fast as well, right? Because I always access from the top in a vertical stack. So accessing, either I can pick will just pick at the value, it will not remove the value, but if I want to detach it from the top, I can use pop, and both are O of 1, right? Because I know where the top is, I just need to pull the value or just see the value. Let's say I want to see the values now. Okay, so I'm just going to iterate over the values, and the iteration obviously be going to be O of n, because there are n items. One important thing, the axis you can see here is I can only pop from the top of my vertical stack, right? I cannot access what is the 5th element or what is the 7th element. I cannot do that, so it doesn't provide random access. Who provides the random access? Only the arrays do that. ArrayList or array. So iteration, I have to loop the stack until it is empty. So while it's not empty, I will keep printing the values. Okay, so I'll pop the value and print it. So how it will work is I'll iterate over it. I will pop the top value. So this is a vertical stack, as we said. So it's going to pop the Wi-Fi router first because that's the most recently purchased item, and then go to the next iteration. What is on the top now? It's the lightning cable. So it will show that value, then it will pop Samsung S3, and at the end portable charger. Let's see the execution. Awesome, you see that? Pop the Wi-Fi router first, that's my most recently purchased item, then lightning cable, Samsung S3, and portable charger. So anytime you want to show or store the values in most recent order, then you use this stack. Now let's talk about the tree data structure, which is one of the most important data structure. Tree data structure has the hierarchy between the items that we store. This is still used to collect or to store the multiple items. So in tree data structure, we have something called the node, and each node, which is basically the item, each item has one or more child nodes. Right, so far the data structure that comes close to the tree is the linked list, right? Because in linked list we talked about each item having a pointer to the next item, but that's one-to-one relation. But in the tree data structure, one item can have pointers to multiple child items. The most widely used tree is the binary search tree, and in binary search tree each node has at max 2 child nodes, and the tree is shorted, meaning that everything on the left of that tree root node is smaller value, and everything on the right of that root node is the bigger value. So that's how the binary search tree is structured. Let's see the example, right? So here you can see that my root node is 5, and on the left I have 3. 3 is smaller than 5, and on the right I have 9. 9 is bigger than 5, right? So it's already sorted. Everything on the left is smaller, everything on the right bigger. For 3 again, 3 has a left node 1, which is smaller than 3, and it has a right node 4, which is bigger than 3, and that is again sorted. And for the right node 9, it has only the left value, and which is smaller than 9. The traversal becomes a little complex here compared to our other data structure, right? Like in the list data structure, the iteration goes from left to right basically, or right to left, or top to bottom, whatever it is, just linear. But here the traversal could be of multiple types, right? It could be 1, 3, 4, right? Because it's multiple relations here. Or it could be 1, 4, 3, or even 3, 1, 4. So there are 3 different ways of traversing a binary search tree. To get the data in the sorted order, we have to do the in-order traversal, which is left node, root node, and the right node. Right, so if we talk in terms of the whole tree here, it would be 1, 3, 4, so that's the left node of 5, then goes to 5, right, and then goes to the right node. Even in the right node I have to go again from left, root, right, so it would be 6 and 9. So the whole traversal is going to be 1, 3, 4. The left node is done, then the root node 5, and on the right node again I do left, which is 6 and 9. Sounds good? Now adding a number is not linear here, right? Like in case of the list, if I have to add a number I just append it at the end. But here, since this has to be sorted, if I add, for example, 7, right, I cannot just add it to the end of 6 or 9. It has to be sorted, right? 7 has to be between 6 and 9. First it starts from the root, 7 is bigger than 5, so it totally skips the left side of the 5 because I know that everything on the left side of 5 is smaller than 5. So 7 is bigger than 5, so I have to go towards the right. So then I have 9. 9 is bigger than 7, right? Or 7 is lesser than 9. So that means I have to go to the left and have 6 here, and 7 is bigger than 6, right? So 7 is going to be on the right node of the 6 here, right? So that's how the insertion becomes a logarithm n, because every time I keep traversing half of the tree. So now let's see the example in Java. Java has two implementation of the binary search tree. The first one is the TreeSet and the second one is the TreeMap. Let's see the example of TreeSet. So TreeSet of integers, and let's call it score tree. Okay, I want to store the scores students have in a class, and I want to show them. The first operation I want to do is add. So let's say I add 3, I add 1, I add 5, I add 7, I add 8, and I add 9. Oh, let me do it the other way. I add 9 first and 8, and I add 1 again. And keep in mind, this is a TreeSet data structure, right? So there will not be any duplicates in it. That's why it's a set data structure. If you remember, we talked about set previously. So how will the implementation work, right? Let's see the visualization. So the first one I added is 3. Okay, so that becomes my root node. Then I added 1. Okay, I add 1. It goes to the left, right, because everything smaller will be on the left side. Then I added 5. 5 should be on the right node. Then I added 7. 7 should be on the right of 5. Okay, awesome. Then I added 9. 9 should be on the right of the 7. Okay, then I added 8. 8 should be on the left of 9 because it's smaller than 9. So each time I add something, I have to traverse half of the tree, so it's logarithm n. And if I want to access the value, can I randomly access the value? I cannot. But Java provides actually a way to access the first value, and also provides a way to access the last value. Let's print those values. The first one is 1 here, and the last one is 9 because this is shorted. Right, first is 1, last is 9. And the complexity of this is O of 1. There is also a way to get the subtree, which is by headset. let's say I want all the elements smaller than 5. Okay, so here, what is smaller than 5? 1 and 3. So if I assign it to a value, whatever element 5, var here is type inference, it gives me shorted set. Okay, and now I can print the first and last of the headset. Okay, so headset gives a value up to 5, it doesn't include 5, so it should be 1 and 3. There is also a way I can get the tail of the tree, and that is by using TreeSet. Okay, so if I want a value bigger than 5, so that is going to be shorter set of integer, it's element bigger than 5. Now I can traverse the whole tree, which is going to be O of n complexity. And how can I do that? Is I can use for loop, int x on score tree. Okay, and I just print the x. So you can see 1, 3, 5, 7, 8, 9. The next implementation of the tree data structure in Java is called TreeMap. The difference between the TreeSet that we just touched and the TreeMap is that in the TreeSet, the tree is binary search tree, meaning that it is shorted, the values are shorted in the tree, but it is not necessarily balanced. And the definition of balance is the number of nodes or the items on the left subtree of a root node and on the right subtree of the root node. They need to be balanced, and the difference of the height of the left subtree and the right subtree can only be maximum 1. That's when we can consider it balanced. So let's see the example of our previous tree in Java, which was the TreeSet, and our tree was like this. Here you can see that the right subtree of 3 here is way heavier than the left subtree where there is only one element. So to remove this kind of weight balance, we have the balance of tree algorithms, and red-black tree is one of those algorithms where the tree balances itself. So the same binary search tree here can look like this if we use a red-black tree algorithm. So how the red-black tree algorithm works. There are a bunch of rules with the red-black tree algorithm, and the first one being that the root node is always black and its children node will be red, but there cannot be too much redness in its children. Right? If there is too much redness in the children nodes, then I need to rotate the tree so that it becomes balanced. So let's try the same example of the tree we tried in binary search tree. So in the binary search tree, we had 3, 1, 5, 7, 9, and 8. Okay, so let's add 3. So it becomes the root node and it's black. Then I add 1. 1 is smaller than 3, so it becomes the left node of 3, but it's the children node. So children node has to be red. So far so good. Then I add 5. So 5 is bigger than 3, so it becomes the right node of 3 and becomes red. Okay, then I add 7. So 7 is bigger than 5, so it becomes the right node of 5. But both are red here, and its uncle 01 is also red. So that means I can turn both uncle node and the parent node as black, meaning that it is balanced up to that point. Okay, so then I add 9. 9 is more than 7, so it becomes the right node of 7, but now there is too much redness here, right? 7 and 9 both are red, so I need to rotate it left so that 7 becomes the root node, 5 becomes the left node, and 9 becomes the right node. Yep, too much redness here, so rotate left, and since 7 is the root now, it becomes black, and its children's become red. So children's becoming red is okay, but children and parent, they cannot be red. Right, so then I add 8. So 8 is bigger than 7, but is smaller than 9. So it goes to the left of 9. Again, too much redness, right? Because children and parent both are red. Right, since both the uncle and the parent were red, it turns them black, but 7 becomes red because the parent node of both black node have to be red. So this is a balanced search tree. And the tree map in Java uses the same technique to balance the tree. Let's see the example. TreeMap, and it's a map, so it has to be key and value, right? So let's say I want to store a map of the number of purchases in a day and the item name. Okay, so it's integer and string. I call it purchases tree equals to new tree map. Now let me add 3 items, and that was Samsung S3. Then I have 1 item, that is iPhone. Okay, then I have, oh, it has to be put. Then I have 3 1, was it 5? Wi-Fi router. I have LG TV. I have AirPods, and there were 8 items sold of utensil set. Okay, so now these are the purchase numbers and these are the items on the right. Okay, so when I add to the map, right? So adding, it's not straightforward as in the regular hash map, because the writing to regular hash map is creating the hash and just writing to the that index of the array data structure. But it's not that straightforward here, because here we have to reorganize the data and balance the tree. So the complexity is O of logarithm n. Okay, now I can access the data using get and providing the key. So if I want to access what is the item that is sold 7 times, I just can use get. But get here will also use logarithm n, because if you know, if I have to find 7 element, what I need to do is I need to see 7 is the bigger number than 3, so I have to go right side of 3, and then I'll find 7 here. So it's not random access to 7, it's a logarithm access to 7, so it's a log of n. I can print that value. It gives me LGTB, right? And there is also a head map function, meaning that if I want all the items those are purchased less than 7 times, I can do purchase tree dot head map 7. It will give me all the items purchased less than 7. Okay, it's called sorted map now. If I want all the items sold more than 7 times, then I can do tail map 7. Okay, if I want to include 7, then I can do true. By default it doesn't include 7, it's more than 7 only. Now I can traverse the whole tree using just a regular for loop. Each entry is going to be map.entry, just like in hash map, and this is going to be type integer to string. Then I'll call it key value, and I will iterate over the entry set, and if I print it, key value dot get key plus key value dot get value. So the traversal now should give me the sorted order. Okay, the first one should be iPhone, second one should be Samsung, so that way I can get the purchase items in ascending order. Awesome, right? So here you can see that I use that map for the lookup using logarithm n complexity, but also I'm able to get all the items in sorted fashion. So that's all about the tree data structure. So that concludes our second lab. Just to summarize, we talked about the arrays, ArrayList, LinkedList, set data structure. Then we also touched queues, which is the horizontal data structure, and the stack, the vertical data structure. Then we touched the tree data structure, which has 2 implementations in Java, the binary search tree and the balanced search tree, which is the TreeMap. And we also touched the map data structure, which is actually super important. So with that, we end this lab. I hope you learned about the data structure in Java. I know I didn't touch all the aspects, of the data structure because there is much more than what I talk about in this lab. But if there are any questions, please let me know. I'll try to answer your question. Now let's do one exercise. Let's say I have a CSV file. If you don't know what CSV file is, it's a comma separated values. And let's say I have a CSV file that I want to parse and use that information to look up the data. Okay, so my CSV file actually comes from Walmart. It's the real data. And it has the weekly sales for the Walmart for individual stores they have across the United States. And what I want to do for this exercise is we want to give it an input, the store ID and the day, okay? And I want the weekly sales, this third column here, as my output. Okay, so if I ask my software what's the weekly sales for store ID 1 and the date March 26, 2010, it should give me 14,004,429.92. So that's the exercise. So let's get to the Java folder and create a new class. Let's call it sales reader. Okay, so I need a main method. I created a main method. Alright, I'm ready. So you can see I put the file in my src/main/resources folder. That's where my walmart.csv file is. And by the way, I installed CSV plugin into my IntelliJ IDEA to get this tabular format, and if you need the same, you can install that plugin. Otherwise, it will show the data like this, which is the CSV format. I first need to parse the file, and to do that, I'm going to use a Java code here. I need a buffer reader. I'm just gonna call it BF equals to new buffer reader that takes the file reader, okay, and the file name. As you saw, the file is in src main resources/walmart.csv. Let's verify the file name. It's capital W and capital W. Alright, we're good. It's red because it expects to throw an exception. We'll talk about exceptions later, but exception is saying that the file may not exist, right? So it might fail. So it is asking what I'm gonna do. I'm just adding exception to the method signature, so it goes over here, and it's still red, and it needs more exception. So far, so good. Now I need to read the file line by line. So for that, I first define a line, and the first time it's empty. I need to iterate over the file, right? Because you can see the file has 6436 line, right? So I need to read that many lines. So I'm going to say line equals to my buffer reader dot read line, and I iterate until my line is empty. Okay, it's not now, meaning that once it reaches the 6437th line where there is no data, right? So that means it's null data. When it sees null data, I need to stop reading the file. If I go to the first line, you can see the first line is store date, it's just the headers for the data, so I don't need to parse this line. I only need to parse the rest of the data. So what I do is I say if line starts with store, because this one is starting with the store, I need to ignore that line, right? That means if the line doesn't start with the store, then only I do my operation. So this exclamation here means not, meaning that if the line doesn't start with store, then only we start processing the data. So as we said that we want to look up the data for the day and the store ID, right? So imagine every time I ask to look up the data, I have to go through the 6436 lines. That's too expensive operation to do, right? So instead of that, using one of the data structure we studied in this lab, I'm going to cache this data so that I don't have to parse this file every time and search the store ID and the date across these 6400 lines. Okay, so to make that faster, I'm going to use a map data structure, right? Because in a map, I can put my primary key, which is my store ID, and the date as my primary key, and the value as the weekly sales, right? So every time somebody asks what is the sales for this store ID and for this date, I just make a primary key out of that store ID and the date and look up the value. And you know that the lookup time for the hash map is O of 1, that is constant time, and that makes it super fast. Alright, so how do I implement that? Is I read each line, and so when I read this whole thing, I parse it. First is I split the line by comma. As you know, the values are comma separated, and I take the 0th index as my store ID, first index as my date, and second index as my weekly sales. Okay, so these are my split values, which gives me an array. Okay, now from the array, I take first index as my store ID. Okay, and I take my day as first index. Okay, and my sales is second index. Alright, so as you know that the sales is floating number here, so instead of a string I'll call it a float number, and I need to parse the string into float number using float.parse float and provide the value. So that gives me sales. Now, as we said, we are going to create a hash map for this, right? So let me call this map, and this is going to be string to double or float, because it is store ID and the day as my primary key and sales as a value. Let's call it per day sales. New hash map. I initialize the hash map. It has no records now. So now every time I read the line from this file, okay, I read this line and I put the values in a map. Alright, so per day sales, the put, and you know the hash map needs key and value. So what is our key? Is the combination of store ID. I'm concatenating them with the underscore. So it's the combination of a composite value of store ID and the day. Alright, and I call this a key, primary key. Okay, so my key of the hash map is a primary key, and the value is obviously the sales. Awesome. So what it does is it reads the file, parses each line, and puts each line as a key value data in my hash map, and done. So when it is done, let's print the value in a hash map. Okay, and as you know, how many records hash maps should have? You know that HasMap has 6436 lines, but the first line is just the headers, so 6435 records. Let's try that. Awesome, 6435. So it's loading the data properly.